Have you ever stopped to think about what's actually ticking inside the smart thermostat on your wall? Or that industrial robot on a factory floor? What about that huge network of IoT sensors that are, constantly monitoring our world? Well, there's this tiny, really powerful brain at the heart of it all. It's a specific kind of chip that basically makes our modern connected life possible. So today, we are going to dive deep into one of the most popular and powerful families of these chips, the STM32. We're going to explore everything, from its core architecture to the software that brings it to life, and we'll even see how it's used to build some seriously complex, real-world systems. So let's get started. All right, so here's the game plan. First, we'll get a sense of just how big this STM32 family really is. Then, we're going to pop the hood and look at the hardware to understand what makes it so fast. After that, we'll jump into the software that unlocks its potential, tackle some advanced design challenges, and then see it all in action in a real project. And finally, we'll map out the next steps for you to become an STM32 expert. First up, let's get a handle on the sheer scale of the STM32 ecosystem. And I mean, it's not just one chip, it's this massive, sprawling family of microcontrollers, and they're designed for pretty much every application you can possibly imagine. Okay, this table really shows you the incredible diversity we're talking about. For example, let's say you're building a battery-powered sensor that needs to last for years. Well, you'd probably look at the STM32L series. It's totally optimized for ultra-low power, often built around an efficient Cortex-M0 Plus or M4 core. But what if you're building a high-speed data processing device, maybe for real-time audio effects? Then you'd turn to the STM32H7 series, with its beastly Cortex-M7, sometimes even a dual-core processor. And for everything in between, from consumer gadgets to industrial controllers, there is a specific series designed for that job. The big takeaway here is that you don't have to compromise. You can pick a chip that's a perfect match for your project's needs, cost, power, and performance. Now, it's also really important to understand a key distinction here. Most STM32s are microcontrollers, or MCUs. They have a Cortex-M core, and they are absolute masters of real-time control, with peripherals like analog-to-digital converters and timers built right onto the chip. But ST also makes microprocessors, or MPUs, like the STM32MP1 series. These guys use powerful Cortex-A cores and include a memory management unit, or MMU. And that MMU is crucial because it's what lets you run a full-blown operating system like Linux. So think of it this way. An MCU is like a specialist, say a traffic light controller, designed for one specific real-time task. An MPU, on the other hand, is like a general-purpose computer on a single chip, capable of running multiple apps at once. Okay, now for the fun part. Let's peel back the layers and look at the hardware itself, because to really get the most out of these devices, you have to understand their internal architecture. It's a whole system designed for one main goal, moving data where it needs to go as fast and as efficiently as possible. So this block diagram might look a little complex, but trust me, it's our roadmap to understanding the STM32's performance. Let's break it down. Over here on the left, we have the masters. These are the parts that can kick off data transfers. That's our Cortex core, the main brain, and the GPDMA, which we'll get to in a sec. On the right, we have the slaves, which are the destinations for that data. Things like our flash memory, SRAM, and all the different peripherals. But the crucial piece linking them all together is this block right in the middle, the bus matrix. You can think of it as the central nervous system of the entire chip. The bus matrix really is the unsung hero of the whole STM32 architecture. I want you to picture an incredibly fast and intelligent telephone switchboard. It lets multiple bus masters, the devices starting the conversation, talk to multiple bus slaves, the devices responding like memory, all at the same time. This is what prevents bottlenecks, and it's really the secret to the STM32's high performance. So, here's the key idea, the real game changer. Both the CPU and the direct memory access, or DMA, controller are bus masters. This is huge. It means the CPU can be deep in some complex calculation, say running a control algorithm, while at the exact same time, the DMA controller is independently shuttling a stream of data from a sensor straight into memory. These two things are happening in parallel. The only time they might have a conflict is if they both try to access the exact same memory location on the exact same clock cycle. And in that rare case, the bus matrix just acts like a referee to decide who goes first. This ability to do two things at once is what lets an STM32 handle really demanding real-time tasks without breaking a sweat. Let's focus on that DMA controller for a minute. It is essentially a dedicated coprocessor, and its only job is to move data. It's like having a specialized delivery service built right into your chip. I mean, think about how inefficient it would be if a CEO had to stop all their strategic planning just to personally deliver every single memo. It's the same thing with the CPU. Instead of having to pause its important work to painstakingly move data byte by byte, it can just delegate that whole job to the DMA. This frees up the CPU to focus on what it does best, executing your application's logic. This timing diagram actually shows us this step-by-step process of a single DMA transfer, right down to the individual clock cycles. It all starts with the request phase, where a peripheral asks the DMA for service. That takes one clock cycle. Next up is address computation, another single cycle where the DMA figures out the source and destination addresses. Then comes the main event, the bus access phase, where the data is actually moved. This can take a few cycles. And finally, the whole thing ends with a one-cycle acknowledge to signal that the transfer is complete. The entire process is just a super streamlined hardware-level operation designed for maximum efficiency. But of course, in a real system, you'll often have multiple peripherals all needing to move data at the same time. And this diagram shows exactly that scenario, with two different DMA channels competing for the bus. This is where the DMA arbiter steps in. If you look at the timeline, both Channel 1 and Channel 2 make a request. The arbiter checks their priority, which is something you set in your software. In this case, Channel 1 has a higher priority, so it gets access to the bus first to finish its transfer. It's only after it's done that the arbiter grants access to the lower priority Channel 2. This priority system is absolutely critical for making sure that time-sensitive data, like an audio stream, doesn't get delayed by less important background stuff. Okay, but incredible hardware is only half the story, right? Now we're going to explore how software unlocks the full potential of that architecture, moving us from simple, single-threaded code up to powerful multitasking systems. So imagine a really simple task. You want to blink two different LEDs at two different rates. In a basic bare metal program, this is surprisingly tricky. Your code runs sequentially, one line at a time. So if you use a delay function to pause for one LED, the entire processor stops and the other LED is completely blocked. This is what we call blocking code. And this is the exact problem a real-time operating system, or RTOS, like FreeRTOS, is designed to solve. With an RTOS, you can write the code for each LED as a separate, independent task. The RTO scheduler then acts like a super-fast manager, switching between these tasks hundreds or even thousands of times a second. To you, it just looks like they're running at the same time. This concept of concurrency is the foundation of pretty much every modern, complex embedded application out there. And creating a task in FreeRTOS is a really straightforward, structured process. First, you define a handle, which is basically an ID for your task. Second, you write the function that contains the task's actual code, its infinite loop. Third, you define its properties, like its name, its priority, and how much memory or stack space it needs. And finally, you just call the creation function, which adds it to the scheduler's to-do list. Okay, so what if your task involves some heavy-duty math, like analyzing an audio signal or filtering sensor data? Well, writing those algorithms from scratch is tough, and that's exactly why we have CMS ISP. It's a free, highly optimized library from ARM that gives you a huge collection of ready-to-use digital signal processing functions, all tailored specifically for Cortex-M processors. And hey, you don't have to take my word for it. As this developer diary from Klangstrom points out, the reason to choose CMS ISDSP is simple. It is highly optimized, and it's already part of the standard STM32 development ecosystem. It's really the industry standard tool for this kind of work, and it'll save you countless hours of development and debugging. Now that we have the hardware and software foundations down, let's start building on them. We're moving into some more advanced topics now, like connecting our devices to a network and managing the complexity of modern multi-core processors. Some of the more powerful STM32H7 series chips actually feature two cores, a high-performance Cortex-M7 and a real-time focused Cortex-M4. This is fantastic for separating tasks, right? Maybe the M7 handles a user interface while the M4 runs a motor control loop. But this raises a new challenge. How do you get these two cores to talk to each other safely and efficiently? This whole process is called inter-processor communication, or IPC. So how is this actually done? Well, the most common method uses a region of shared memory that both cores can access. On the STM32H7, this is often the SRAM4 region. And the really clever part is that this memory is in its own power domain, so it can stay powered on even if one of the cores goes to sleep. Inside this shared memory, you create two ring buffers. I want you to think of them as circular conveyor belts for data. One buffer is a one-way street for data going from the M7 to the M4, and the other is for data going in the opposite direction. This asynchronous fire and forget method is super efficient and avoids the need for complex locking mechanisms, which could otherwise cause one core to get stuck, waiting for the other, leading to a system freeze or deadlock. All right, let's talk about networking. Getting an STM32 connected to an Ethernet network usually involves a lightweight TCP/IP stack called LWIP. But for a professional application, just getting it to ping isn't enough. You need to optimize for performance. And as this table shows, that means diving into the configuration files and tuning some really low-level parameters. For example, TCP_MSS stands for maximum segment size. It defines the largest chunk of data that can be sent in a single packet. Tuning this and the related buffer sizes is the difference between a simple demo and a robust, high-performance web server that can handle a ton of data without dropping packets. Okay, we have covered a lot of individual concepts. So now let's see how they all come together. We're going to walk through the design of a complex, real-world embedded project to really connect all the dots. Our project Spotlight is a digital oscilloscope. This is a classic, really challenging embedded project because it forces you to master the entire signal chain. You have to acquire an analog signal at very high speeds, process all that data in real time, and then get it ready for visualization. It is a perfect test case for everything we've talked about. This diagram shows the complete data flow, and you can see how all the pieces we've discussed just click into place. It starts with the analog signal, which gets sampled by the analog to digital converter, or ADC. Now this is happening at a very high speed, generating a ton of data. So instead of bogging down the CPU, we use our delivery service, the DMA controller, to automatically transfer every single sample from the ADC directly into a memory buffer. This all happens in the background. Once a complete waveform is captured, the DMA notifies the CPU. The CPU then wakes up and uses that powerful CMSIS DSP library to perform a fast Fourier transform, or FFT, on the data. This is the heavy math that turns the raw signal into a frequency spectrum, which then gets sent to the display. You see, each part of the system is doing what it's best at. And this really shows the power of using a good software library. The fast Fourier transform is a seriously complex algorithm. I mean, implementing it from scratch and optimizing it for the hardware would be a huge project all on its own. But with the CMSIS-DP library, all of that complexity is just abstracted away into a single function call, ARM RFFT Fast F32. This is a perfect example of why these libraries are so essential. They let you leverage the work of expert engineers, so you can focus on the unique parts of your project instead of reinventing the wheel. Wow, we've journeyed all the way from the core architecture to a complete system. So the question is, where do you go from here? Let's wrap up by outlining a clear roadmap for you to continue learning and actually start building. Okay, here are your next steps. First, just get comfortable with the official tools. STM32 Cube IDE for writing your code and CubeMX for graphically configuring your chip's peripherals. Then, build a simple project using FreeRTOS. Seriously, blinking those two LEDs is the perfect place to start. From there, explore the CMSIS DSP library with an audio or sensor project. And finally, challenge yourself to implement a simple communication protocol like sending data over a serial port. Each step builds on the last, and it'll really solidify your understanding. So we've seen how the parallel architecture of the bus matrix and DMA allows for incredible data throughput. We've explored how an RTOS can bring order to complex concurrent tasks, and how libraries like CMISS DSP can handle the heavy lifting of complex math. We even put it all together in a real-world project. You now have a solid map of the STM32 ecosystem. So the only question left is, what problem will you solve first?
If you like this one, the YouTube algorithm says you're gonna love my other videos, so go check them out.